All right, everyone, welcome. This is a focused explainer, and it's designed to be the perfect final review for your radio communications course. We are going to lock in all those key concepts you absolutely need to know, so let's just get right to it.
So, let's start with the big question, right? The one that drives absolutely everything we're going to cover today. If you can answer this, you've grasped the core of radio communications. And believe me, by the end of this, you'll be able to explain it from top to bottom.
Here's how we're going to tackle it. We've got 4 main stages. We're going to build your knowledge from the ground up, just like you would build a real system. Each part builds on the last, so really pay attention to how all these ideas connect with each other.
Okay, let's dive into Section 1. This is all about the physics, the stuff that makes everything else even possible. You can think of these as the absolute ground rules for every single wireless system out there.
You've got to understand the spectrum. It is the foundational resource for all wireless tech. Seriously, think of it like a giant highway for information. All the different services we use, broadcast radio, Wi-Fi, satellites, they each get their own lane, their own frequency, so they don't crash into each other.
Now, the decibel, you're going to be using this concept constantly. And here's why it's so great. It lets us work with these huge, massive ranges of power without our heads exploding. Instead of juggling enormous numbers, we just use a simple logarithmic scale. Now remember this, a 3 dB gain means you've doubled your power. A 10 dB gain, that's 10 times stronger. That is a critical shortcut for any calculation you'll do.
Okay, this slide shows something so important. When we talk about a clear line of sight, we don't just mean a straight line like a laser beam. No, it's a whole 3-dimensional space, kind of shaped like a football, that you have to respect. If objects get in that zone, waves can bounce off them and mess up your signal at the other end. So the main takeaway, you've got to keep this zone as clear as possible.
So let's test that idea with a real-world problem. This is exactly the kind of thing you'd see. You've got a tree in the way, and only 40% of that first Fresnel zone is clear. Is the link going to work? The short answer is, no way. It's not viable. For a link to be reliable, you need at least 60% of that zone to be clear. And honestly, you want even more. 40%, you're going to have some serious signal problems.
All right, so we've got the physics down. Now let's move on to the actual components. This section is all about the hardware, the physical gear that makes all that theory come to life.
These 3 right here, these are your essential tools of the trade. They're what you use to diagnose, check, and maintain pretty much any radio system. The signal generator, well, it generates test signals. The field meter goes out into the real world and measures how strong those signals are. And the oscilloscope? That lets you actually see the waveform to check its quality and look for any problems. You've got to know what each one does.
Okay, let's apply what we know. Here's a practical scenario for you. You need to get a signal across a rural area, but there are hills and trees in the way. This is exactly the kind of thinking you'll do in the field. So, what's the right antenna for this job?
And the answer is a directional antenna, like the Yagi you see here. Its whole design is about concentrating all that radio energy in one specific direction. It's perfect for punching that signal through or over obstacles, instead of just wasting power spraying it everywhere.
Now, what about a totally different challenge? Let's say you're trying to pull in a super weak signal from a satellite that's thousands of kilometers up in space. The needs here are completely different, right?
For that, you absolutely need a parabolic dish. The reason is all about high gain and super precise alignment. That dish shape acts like a giant funnel for radio waves. It collects that faint signal over a huge area and focuses it all down onto one tiny little point, your receiver. It's really the only way you're going to get a usable signal from that far away.
Okay, so we've got the waves and we've got the hardware. But how do we actually put our information, our voice, our data, our video, how do we get that onto the radio waves so they can travel?
Well, that is where modulation comes in. It's the magic trick that makes this whole thing work. See, a pure radio wave, a carrier wave, doesn't actually carry any information. Modulation is the act of changing something about that wave, like its height, its amplitude, or its frequency, in perfect sync with our information signal. It's literally how we write our message onto the wave.
And that brings us to the classic engineering trade-off, AM versus FM. Amplitude modulation, AM, is way simpler to build, but it's really easy for noise and static to mess it up. Frequency modulation, FM, is more complicated, but it gives you way better sound quality because it's much tougher against interference. That's exactly why your favorite music station is on FM radio.
So these techniques are the absolute building blocks for pretty much all modern digital communication. Instead of a smooth analog signal, these methods encode digital bits, ones and zeros, by shifting or keying a property of the wave. And that's exactly where their names come from: amplitude shift keying, frequency shift keying, and phase shift keying.
All right, for our final section, let's take everything we've just talked about and see how it works on a massive scale. We're looking at one of the most incredible applications of all this: satellite systems. This is where waves, components, and modulation all come together globally.
This table here lays it all out perfectly. It shows you exactly how a satellite's altitude, how high up it is, directly affects its latency and what it's best used for. Geostationary, or GEO, satellites are way up high. They're great for TV broadcasts because they stay in one spot, but they're just too far for fast internet. MEO, medium Earth orbit, that's the sweet spot for things like GPS. And LEO, low Earth orbit, is nice and close, which is perfect for low latency broadband.
And this quote right here, it gets to the heart of it. It explains exactly why these new satellite internet constellations use low Earth orbit. It's all about latency. That's the delay for the signal to go to space and come back down. For things like video calls or online gaming, latency is the enemy. By being closer to Earth, LEO satellites keep that delay to a minimum.
So, as we wrap this up, here's what I want you to remember. Radio communications is a field that is all about trade-offs: simplicity versus performance, coverage versus how many people can use it, cost versus capability. Understanding these fundamental choices is the real key to mastering this subject. Good luck with your review, and you're going to do great on that test.